of some kind. It'll be subcritical flow, it'll be supercritical flow. It might be, if you're in supercritical, and it doesn't have to be a log, it'll just be responding to something. So it might be, I have a stream bottom that looks like this. I'm in supercritical flow. How do energy and stream respond? I'm in subcritical flow. My stream goes over a big step. How do stream energy and water depth respond? Okay? So just think of simple scenarios and how subcritical flow responds and how supercritical flow responds. So for example, this, you'd be gaining energy, wouldn't you? Because you're going off a cliff. You're trading potential energy for kinetic energy. And so the streams would actually gain energy, and the height above the bottom of the energy dashed line would be greater, would get greater coming down here. It's like
so you're going like this?
No, it wouldn't be going up because water flows downhill, right, but it would get higher above the stream. It would be one thing that would happen. So this distance would get greater. It'll never go up. You can't actually be, because you're adding the energy by dropping elevation. And so it'll never go up, but it can get higher above the bottom of the stream. It can. So, and that's actually why you get rapids and supercritical flow. You're going down a steep hill, so the water accelerates enough that it becomes supercritical.
And that would happen in supercritical then?
Why don't you guys play with that and see? See what happens. Take that little diagram, and now we're adding energy, and see how supercritical and subcritical would respond. Just for fun, play with it. Anyway, and so here's, and we basically went through this exercise just now. Draw the surface of the stream, and usually I'll just give you some point. I'll say at this end of the diagram it's here, and at this end I'll give you like a, sort of a rough drawing. And at this end, so here's water level on this side, and I don't know, there are 2 toxic waste barrels in between. So something simple like that. So you can see, and so you then trace the water depth, and then you trace the energy as a dashed line, with that being the extra energy due to velocity. So the higher the velocity, the bigger the distance between the stream bottom and the top. And then you can show the velocity. The only other thing to add is to show the velocity of the water with arrows. Everybody got it? All right. This will show that you really understand this. All right. How are we doing? We're doing good. One of the things we've noticed is that as you go downstream, streams lose energy. Waves lose energy on a beach. And I'm going to skip through this because I don't want to spend a lot of time on this, but you can feel free to do it on your own. The energy, let's just pretend we have a pipe, a hose. And in that hose, I've got water coming through. You can calculate the amount of energy in that fluid. It's flowing at a certain velocity through the hose. It's got a certain amount of pressure to it, and that pressure, if we have, and usually the experiment I do is that I don't do in class anymore because I kept making huge messes, was that the hose would, I keep moving these things over here, the hose would have enough pressure, we'd have a hose, we'd have a little pipe coming, a little clear glass tube coming up, and then we'd go another meter, and then we'd have another clear glass tube. And so you could see that the water level in this hose was less than this hose. And so it's the pressure in your hose or pipe, it's pushing the water up here, and you can see it's losing energy as it flows down the pipe. Everybody okay with that?
Mm-hmm.
Anyway, and so you can actually measure, just by doing this here, we can actually measure the energy in that pipe. It's got enough pressure to push it up that high. It's going this velocity, and it has this much area. So that's how much actual energy is in the water. Can do the same, and because this is a pipe coming out of a sink, the amount of water going down the pipe, the discharge, and the velocity are the same. They don't change. And the thing that changes as the water goes down the stream is the energy in the water. But this water is flowing at the same velocity as that water, right? And if I made another one, it would be the same distance down. So as long as the pipe stayed the same, the loss in energy, the resistance to flow, would be a constant that's related in somehow to the velocity. The higher the velocity, the faster you lose energy. And in fact, it's related to the kinetic energy of the flow. How much, so the square of the velocity. So if I double the velocity, I quadruple the resistance to flow. It takes 4 times, I lose energy 4 times faster if I double velocity.
So in that little experiment right there, if you doubled the velocity in there, you would notice
the pressure difference would get 4 times bigger.
So if you lowered it,
Pressure differences would reduce by the square root of.
It's like misters on your porch. You barely turn on the hose. The last mister's not going to have as much oomph coming out.
As much pressure. Once I tried to I was trying to use hydraulic power to drill a well, and I had to run like 200 yards of hose, regular garden hose. By the time I got to the end, it was barely dribbling out.
Yeah.
Because the pressure at the top wasn't enough to push it all the way down. Okay. Anyway, so here's just, and you guys don't need to remember these, but basically, this just says that the cross-sectional area times the density times gravity times the change in pressure is equal to the energy in the hose, the pressure force in the hose. And so the pressure in a hose is related to the amount of the area of the hose. A bigger pipe has a lot more energy than a little tiny pipe. And the pressure loss, so the size of your river, say, gives you the energy. The pressure loss is due to drag on the sides of the hose or on the bed and banks of a stream. And basically, the energy lost is proportional to the wetted area and the distance you go. The farther you go, the more energy you lose. The more area that you've got to drag along, the more energy you lose. And I'm going to skip this again too. You could do these calculations on your own if you feel like it. And here's where I do it for some of those calculations. So I'll let you guys play with them. Okay. You can calculate shear stress on different equations or different settings, and people do that. What all you have to do, right, is measure that loss in energy and relate it to velocity, to the density of the stream, and if we do it for an open channel flow which is basically a canal or a river, the elevation loss, the energy loss in the stream, is equal to the velocity squared. We already figured out that would be the case. So the faster it's flowing, the faster it loses energy. The density of the fluid, because that's proportional to density. And this here. And what that is a shape and roughness factor. If you have a U-shaped channel or a V-shaped channel, most natural streams you can approximate with a half a rectangle. 2 banks and a bottom. That's if you actually try to fit a rectangle to most natural streams, that's what they come up like. And so the F over 8 counts for that, and then it counts for what's on the bottom. Is it a nice smooth bottom, or is it full of toxic waste particles? And the rougher it is, the bigger this number is, the more the energy loss for any given velocity. How are we doing for time? We still got 5 minutes. This here, this term, Dr. Pavlis has probably given it to you. It's called shear stress.
Mm-hmm.
And his shear stresses were megapascals, right? Where rocks are dragging across other rocks. Here we just have water dragging on the bottom of a stream, but it's the drag of water on the bottom of the stream. And that does 2 things. As the water's going along, the stream is dragging on it, and that slows it down and causes it to lose energy. So the surface of the water gets lower, and the stream doesn't keep accelerating till it's going infinitely fast. Same thing happens on the bottom. The bottom of the stream has the water dragging over the top. It is dragging and pulling at the bottom of the stream, partly with the Bernoulli factor, and that is what causes sediment to erode and sediment to be transported down the stream. So this here is what causes sediment to be moved in nature. Okay, questions? Everybody good on this? Okay. So we can calculate the roughness on our pipe, and again, and basically, this is basically how they figured out these F values. They just actually went to natural streams and different places and said, okay, here's our velocity, here's our depth, here's our water density. How much energy does it lose? And they can estimate, or pretty well calculate, the amount of energy used. They usually, by looking at the change in elevation of the water, how much did it lose elevation, and then the change in cross-sectional area and depth. So you can actually measure all those things, and so what you do is you measure the velocity, you measure the density by using a temperature, or you can actually probably weigh your water if you want to. You know how much energy is lost, so you know what the shear stress is, and then you can use that to calculate the roughness factor. And so people have come through and sort of empirically come up for natural channels with all these different roughness factors. This roughness factor here is called the Darcy-Weisbach friction factor. And there are 3 or 4 different kinds of friction factors that engineers use. You won't have to calculate any of these because, as I say, they do them by actually making lots and lots of measurements. And I will give you reasonable estimates for them. Okay, And that is a good place, because I can start off tomorrow with lots of boundary layer, not tomorrow, on Wednesday with lots